Okay, tonight we have with us on our seminar Marko Ristić. He is a PhD student at Rochester Institute of Technology, and he will tell us something about models and parameters of kilonova AT2017gfo. Marko, the floor is yours.
Thank you, Bojan. So yes, let me actually, get the WebEx out of the way. Okay, yes, so like Bojan said, I'm a PhD student at RIT. That's in Rochester, New York the state, unfortunately not the city. I work closely also with collaborators at the Los Alamos National Laboratory in Los Alamos, New Mexico in the southwestern United States. It's most famous for its development of the first atomic bomb. And today I'll be talking about kilonova modeling, some interpolation techniques that I use to make it computationally inexpensive, and like Bojan said, how we compare to the event AT2017gfo, which if you have not heard of, I'll discuss in a little bit of detail. So to start the outline of the talk, I'll go through some kilonova background. For the interpolation that I do, we first look at light curves of kilonovae, and then do some parameter inference with our light curve models. And then we generalize to spectra and perform the same. In both our light curves and the spectra, we find that we have an underluminosity problem in blue wavelengths, so we're not quite able to produce enough flux. So I'll highlight that, and then I'll talk about some current attempts at a solution, which have unfortunately shown to not be as successful as we would have liked. And then some comments on future work for next steps, and then next steps at solving this problem that we've identified. Okay, so to start, how do we create the systems that actually make a kilonova? So first, we start with a zero-age main sequence binary in the top left panel. We have the primary is on the right, it's this pink colored star, and then the secondary is this red colored star. And since we're ending with a double neutron star system, we can assume that these two stars are going to have at least roughly 8 solar masses each. We call the one on the right the primary because it's going to evolve sooner, meaning it's going to go up the red giant branch first. And as it does that, it's going to grow in radius and it's going to overflow its Roche lobe such that we have mass transfer from the primary going on to the secondary. In the third panel, what we see is that the outer layers of the primary have been transferred onto the secondary such that the secondary is now more massive. And what we see is the inner core, basically the inner parts of the star closer to the core where it's hotter, and that's why it's shown as blue. The primary then undergoes core collapse supernova type 1 or 1b or c, and we're left with, in the fifth panel, a neutron star as for the primary, and the secondary is still a zero-age main sequence star. As the secondary then starts evolving, it's going to also ascend the giant branch, and there's going to be essentially mass transfer onto the primary. But this time, because the primary is now a compact object, the envelope of the secondary star is going to encompass it, and they're going to have a shared common envelope. And then if you've heard of the analogy of an ice skater as they're spinning on ice, when they have their arms out and they move them closer in, they start to spin faster. Effectively, the same thing happens in this system where the neutron star is dragging along the material in the common envelope, and it's moving closer in. The binary separation is shrinking, and therefore the angular momentum is increasing, and this increase in angular momentum is actually going to expel the envelope, and now we're just left with a neutron star primary and the hot interior star, still a zero-age main sequence. Nothing's happened yet, but it's still, we're just again seeing the interior parts of the star where it's hotter and represented by a blue color. Now here at the bottom, this diagram specifically is showing how helium is removed from the neutron stars which are produced. We don't really care about that distinction specifically. effectively what we have is another mass transfer phase where now this, the secondary is transferring mass onto the compact object primary. And as it's losing mass, it's going to puff up. And there's going to be another common envelope, except this time the secondary will just undergo supernova, which strips the envelope, and we're left with 2 neutron stars. So I may have glossed over some details in this. This is not binary evolution is not exactly my field of study. This is just to give you some background on how we can form a neutron star binary. And then if we assume that this neutron star binary is going to merge in a Hubble time, or the age of the universe, over time, it will emit gravitational waves, and the binary will get closer and closer until it gets close enough that it's time for it to merge. And so what I'm showing here is a video of the end stages. This is a simulation by another a student who used to be at RIT. She's graduated since. Her name is Tanmay Gupte. And she made a simulation video of the end stages of the merger. So this is right before merger. This is a top-down view of the binary plane with the x and y axes. And the color scale is log density, where yellow is more dense and blue is less dense. And so what we see here in the end stages of the merger is that first I'll just pause right here and show you that there's significant deformation of the stars as they begin to merge. The star is extremely elongated, and we'll see that that actually turns into the ejection of material in the plane. And of course out of the plane, but since we're just looking at a two-dimensional projection, we'll just consider the plane. We have a merger remnant form in the middle. It's a black hole for the purposes of this simulation. And then if we keep playing, we'll see that a lot of the material settles into this accretion disk around the merger remnant. But then I'm not sure if you can see, but on the blue background, we can sort of see wisps of material also being ejected from the system. So effectively what we have is a lot of the material stays in this accretion disk, but a lot of it is also removed from the system. And now if we think about, so this is material removed from a neutron star, it's going to be neutron rich. And we're interested in quantifying this neutron richness because it has significant impacts on the nucleosynthesis that happens in the ejecta. So the quantity that we're going to use to measure the neutron richness of the ejected matter, which I might refer to as the ejecta, is the electron fraction. And this is simply the ratio of protons to baryons. And you can think about it in 2 limiting cases. So the first limiting case is if we have extremely neutron-rich matter, the YE, or the electron fraction, is going to tend towards 0 because this will effectively be 1 over a very large number due to the number of neutrons. And if we consider the other end of the limit, which is stable matter, where the number of protons and neutrons is comparable, then this will be 1 over 2, which is 0.5. So these are our 2 limiting cases to keep in mind, where extremely neutron-rich matter will have the YE tend towards 0, and then stable matter, much like what we would see on Earth, would tend towards 0.5. The context of this, this quantity and the neutron richness is that if we consider decays, radioactive decays, and for simplicity, we're just going to consider beta minus decay and neglect things like fission and more complicated decays. We can see that beta minus decay is a neutron decaying into a proton, an electron, and an antineutrino. And if we kind of generalize that into the context of nucleosynthesis, we can imagine that if this was some neutron on, for example, a nucleus of some element X, it would have some atomic number A and some proton number Z. And then one of these neutrons would turn into a proton such that the atomic number stays the same, but now we have Z plus 1 protons, meaning that we've created a new element X prime, and of course we have the electron and the antineutrino. But the whole idea is some of these neutrons will latch onto nuclei. There's going to be a lot of neutrons, and in the next slide, I'll talk a little bit about just how that works. But for the purposes of nucleosynthesis, these neutrons, this extreme sea of neutrons which is available, will be used to create new elements from these seed nuclei of, for example, element X. Okay, so the reason why it's important to quantify just how neutron-rich the system is because of the rapid neutron capture process. And in essence, what that's saying is, if you can see this diagram in the top left, the reason why it's called the rapid neutron capture process is that neutrons are being captured by a seed nucleus much faster than they can actually decay. So every tile that we move over is another neutron captured, and every tile that we go up and to the left is a neutron turning into a proton. So here we capture 1, 2, 3 neutrons. There's 2 decays, so we turn 2 of those neutrons into protons, but then we capture 2 more. So the net influx of neutrons is higher. And what we can see is that if we were to do, so this is a nucleosynthesis, a nuclear reaction network movie, and it's basically showing the abundances of nuclei of atomic number A and proton number Z as a function of time. And what we'll see is that we start with some seed nuclei here, which have some abundances. And then when this rain of neutrons occurs, you see that it really branches out sharply to the right, where we get a lot of baryons, but the majority of them are not protons because we have more of the branching out to the right than going upward. And so if what this is really saying is that we have a lot of radioactive nuclei at very early times. This is about 1/10 of a second. And then as we go further in time to the time scale of weeks, we see that this is actually going to want to tend towards stability, and our neutrons are going to want to turn into protons. And once we're at week-long timescales, we're now seeing that the majority of the abundances, which is this greenish line here, has shifted from where it initially was here and moved up and to the left. And so what we saw from the diagram in the top left is that moving up means that protons are being created, and moving left means that we are losing neutrons effectively. So the reason that's important is because that's an integral part of our modeling approach. So our modeling approach has, it consists of 2 components. So let's just look at the diagram on the right really quickly. Again, we have this merger remnant in the middle. In our simulation, that was a black hole. There's this light blue accretion disk, which is formed around the merger remnant. We have a GRB jet, which is emitted on the order of seconds after the merger. We don't include this in our modeling approach at the moment. And then we have these 2 kind of shapes where we have a neutron-rich tidal ejecta, where the main R process happens. So we're going to be calling that the dynamical component. And the reason we call that is because it's generated on dynamical timescales. So the first couple dozen of milliseconds after the merger. And this is the part that we saw in the simulation where the neutron star was being ripped apart and deformed. This is the material that's ejected then. So it's extremely neutron rich. And this is where it's called the main R process because it would follow the nucleosynthesis that happened in the video that I showed on the previous slide, where elements even up to a Z number of 100 were created. So very, very high, very heavy elements, if you will. Then we have the neutrino-driven wind, which is where the weak R process happens. And for our modeling purposes, that's everything else. So that's everything that's not the dynamical ejecta that's formed via this tidal separation process. It's called the weak R process because by the time that mass is removed from the system by way of the neutrino-driven wind, the YE of the system has increased such that we're not getting the full R process, so we're not getting the full nucleosynthesis up to Z equals 100, but some partial amount that depends on the specific YE value. So the main R process for the dynamical component and the weak R process for the wind component illustrate our composition for our models. We have the morphology, which is the shape of these 2 components. This largely influences the observational effects, like depending on viewing angle and things like that. And for our purposes, we just use a torus or a donut shape for the dynamical component along the plane of the binary. And we use a peanut shape, which is 2 lobes, like this purple part, going along the jet axis. We also have two other parameters, the mass and the velocity, which are just assigned numbers in units of solar mass and the fraction of the speed of light. And one thing to note for the velocity is just that we assume that it is not, so our ejecta is not accelerating by the time we model it. It's homologously expanding at a constant velocity. So that was our background, our modeling approach. So now let's get into the computationally inexpensive part of the talk, which is how do we do our interpolation? So as the slide might suggest, we use Gaussian processes, and effectively, so this is just a general from the textbook Gaussian processes for machine learning. This is a useful way to visualize how Gaussian processes work. We have some general inputs x from 0 to 1, and then some general outputs f of x. This is not at all related to this has no physicality to kilonovae. It's just an example figure. And it's effectively saying that if we have some arbitrary inputs x, there are many functions which could model the behavior of f of x. And that's what the left-hand figure is showing. And on the right-hand side, if we say, well, let's put two inputs where we know what the output f of x is for some inputs x at about 0.2 and 0.6, then in that region, the behavior of f of x is constrained and the uncertainty in the nearby region is reduced such that there are still many functions which could describe the behavior of what the data is showing, but they're much more constrained than we saw in the left-hand figure. So what does that mean for us? So what I did was I started with an initial simulation grid, and here I'm showing the 36 simulations that made up this grid. This is the log bolometric luminosity on the y-axis as a function of time and days on the x-axis. And as I mentioned, we have a low YE of 0.04 for the dynamical ejecta, a higher YE of 0.27. So again, these just mean neutron richness. Our dynamical ejecta is much more neutron rich than our wind ejecta. And the morphologies are torus and peanut, as I explained. And the 36 different simulations come from varying the mass and the velocity of each component, where the masses were spread out between 1/1000th and 1/10th. And the velocities had lower and upper limits of 0.05 and 0.3 times the speed of light. And the masses are in units of solar masses again. And so how do Gaussian processes come into play? Well, let's look at, we had this initial simulation grid, but 36 simulations was not enough to model, to accurately interpolate the full behavior of all different light curves that we would get out from our simulation, from the possible inputs to our model parameters. So what if we, for example, this is again a visual aid, it's not representative of light curves or anything, but if we imagine that our 36 initial simulations are these black X's, there are simulation data. And so as in the previous slide, we know the behavior at these black X's, and we're trying to model this theoretical map of inputs to outputs represented by this yellow-green line, which of course in reality and in research we don't know, but this is, this is kind of what we're trying to figure out. And naturally, our interpolation would say that if we have 2 points, the most accurate prediction is just a straight line between them. But we can see that that doesn't match our theoretical map very well at all. So what we want to do is we want to place another simulation, and we want to place it in the region of largest uncertainty such that we know we're getting the most information out of our placed simulation, because again, they are expensive. And this region of largest uncertainty is identified by this dashed vertical line. So if we place a simulation there, we see that the uncertainty in that region has decreased. And hopefully you can see my cursor because I am moving it. But the new simulation was placed at this arbitrary input of 2, and we can see that the uncertainty has decreased there. Now we do the same thing again. We identified that the largest region of uncertainty is around this 0.1 input. So we place one more simulation there and then one more time, and we can do this ad nauseum. But the point is that I'll stop here because the example starts to be very clear. And initially our interpolation output, which is the blue line, was a straight line. But now we're with these 3 additional placed simulations, we're able to actually get a pretty decent, we're much closer to modeling the behavior of the theoretical true map in yellow-green. So the idea is we place simulations repeatedly until we get some sort of convergence, or at least until the uncertainty is at is a quantity that we're happy with. So after doing that, we placed the total simulation grid was about 400 simulations. So we placed about 10 times as many simulations as we started with. And now, again, this is log bolometric luminosity as a function of time and days, and this is just showing the bulk properties of the light curves. So we used the bolometric luminosity for placement of new simulations, but we wanted to see what the interpolation would behave like if we looked at specific broadband filters. So here, for our interpolation test, we change our units to AB magnitudes. It's again, we're just looking at the broadband filters from G through K and the Spitzer 4.5 micron band. But we have AB magnitudes as a function of time and days. Effectively, it's still brightness in days. And what we are showing is if it's just the standard leave one out approach, where we have our training library of simulations, which we use to train the interpolator, the Gaussian process. But we've taken one of the simulations and removed it from the training library. We kept it off to the side as a test. So we know what the light curves for that simulation look like, and we give our interpolator the inputs for that simulation, and we see if those match. If we're able to properly match that, then we know we have successful interpolation. And in fact, we do see that because the Gaussian process output is the solid line and the simulation is the dashed line, and you can barely make out that there are some differences between the two, but the overlap is extremely good. So we are convinced that we're able to interpolate in our broadband filters from G through K, and of S, but we will drop that for the time being. So we're happy. We're confident moving forward that we're able to interpolate on our library of simulations. So what can we do next? What's our next step? Our next step is to compare our models to real data. And so this is what I mentioned before, AT2017gfo. This is, if you haven't heard about it, this is an extremely, I guess, famous event because it was the first event to be measured with both electromagnetic emission on the left and gravitational wave emission on the right at the top. On the left, we see apparent magnitude as a function of time and days. These are the data points with uncertainty bars are the data. And the solid lines are model fits from the Villar 2017 paper. We're going to be most interested, so there was a lot of data taken for this event. The part that we're interested in is just the optical and the infrared, given our choice of filters from G through K. And what we do is effectively say what parameters of our model are going to best match the AT2017gfo observed data. And so this is our best match to that data. We see that the agreement is quite good, so we're able to actually model the kilonova well, which is always a good thing. We have AB magnitudes, again, this time apparent magnitudes on the y-axis and time and days on the x-axis. And as we start from the K-band and move down, we see that our agreement is very good until we get to the G-band. And so this starts to highlight that problem that I mentioned at the start, where we have some underluminosity at blue wavelengths in the G-band. You can see that here at about 2, maybe 3 days, we really start to deviate. At 3 days, we're outside, the data is outside of our uncertainty band, and at 4 days, we're more than 2 magnitudes away from the observed data. So we're really not fitting well at that point. Nevertheless, the rest of the fits are pretty good, and we feel confident in reporting the best fit parameters. And I know I mentioned things like masses and velocities, etc., during the introduction of the modeling approach, but what I want to highlight is just the total ejected mass. So on the left, we have the same plot as on the previous slide. AB magnitude is a function of time and days. And in the middle, what we have is the prediction of the total ejected mass in the log. And we see that with and without the K-band. We remove the K-band from our analysis for a specific reason. I encourage you to visit the paper if you're interested in the details. But we see that in both cases, we predict something like minus 1.4 to minus 1.5 total log ejected mass. And this study by Heinzel et al. 2021 compares the predicted total ejected mass for AT2017gfo from a variety of different models, and we find that we have pretty good agreement with other models in the literature as well. So we're quite happy. Other than this blue under luminosity, our fit is actually quite good, and we're predicting things that other groups are as well. So let's get more general, because light curves are really effectively just a subset of the spectra. What can we do with the spectra? So here what I'm showing is an example spectrum from one of our simulations. This does not match AT2017gfo necessarily. This is just one of the spectra in our simulation library. On the y-axis, we have units of spectral energy density in units of ergs per second per centimeter squared per angstrom. And on the x-axis, we have wavelength in units of microns. And what I'm showing here is 5 different spectra at different times. The times are in days, as indicated in the legend in the top left. Well, we see that initially at about a day and earlier, the spectrum is really just a power law. But then as we get to 3 and especially at 10 days and later, we see that the spectrum does get some very interesting features in it, like these wiggles here in the Y through K bands. So the reason why we might be interested in spectra is because they have more interesting features and they might tell us more about the physics of the system. Rather than using Gaussian processes to interpolate the spectra, we use random forests. Gaussian processes do not scale very well with larger data volume, and the data volume for the spectra was substantially larger than for the light curves. So we used random forests instead. And just a quick overview of what random forest is it's a map of the inputs to the outputs, so the data set to the final result, as follows. It's a collection of decision trees where the inputs are given to one of the trees, and then it creates a series of criteria or decisions to split up the data in such a way that it can map it to the output. So our masses and velocities for each component mapped to the actual spectrum. And then it creates some result. And then this is repeated for every decision tree in the forest, for all n decision trees in the forest. And finally, the result for each decision tree is considered in a majority voting scenario, where the most common answer across all of the trees in the forest is taken to be the final result. And what we see here is, so what I'm showing here is, again, spectral energy density in the same units as before as a function of wavelength in the same units as before. In black, we show, again, this is another leave one out validation. So a test spectrum, which we removed from the training set and kept off to the side. And then we evaluated the random forest at the parameters, input parameters for that simulation, and wanted to see if it matched the true spectrum, which is in black. So black is the test spectrum, which is the true answer, and red is the output of our interpolation. And we see that we get extremely good agreement, particularly in the bands we are interested in from G to K. You might notice that there is some weird behavior here in the G band, and particularly that our interpolation output is less bright than what the actual what the true value is. However, this is just because these are particularly jagged features in the spectrum here. The overall large scale features are extremely well fit, and indeed here past 5 microns we're able to recover even these advanced these more exaggerated features in the spectrum. These may or may not necessarily be real, but it's cool to see that we're actually able to match those to at least some degree of accuracy. With our spectrum interpolation, we can also interpolate in time and angle. So before I showed, here's just a reminder, I showed this plot of the evolution of the spectrum for one of our simulations over time. And we can recreate that with our interpolation, shown in this figure in the bottom left, where for a fixed angle of 0 degrees, we can see what the evolution of a specific spectrum is over time at 1, 4, 7, and 10 days. Likewise, we can fix the time to 10 days, for example, and see how the angles change as we vary the viewing angle starting from the jet axis and looking towards the basically looking from a pole-on view to an edge-on view, where 0 degrees is in line with the jet axis, and 90 degrees is in line with the plane of the binary. So if we try fitting these interpolated spectra to the data, we are now looking, so we still have red and black spectra, except now the red is still our interpolation, but the black is the AT2017gfo data. And this is our fit to the observed spectra of AT2017gfo, assuming just a 2-component model, the same exact approach that we used with the light curves. So we haven't changed anything in terms of our modeling. We're just seeing how well our spectra fit to the data. At 1 day, we see that the fit is quite good. But at 4 days, we start to really see this deviation in the G-band. The rest of the spectrum fits decently well, but there is a large discrepancy in the G-band at 4, 7, and 10 days. Although at 10 days, the data is rather noisy and our fit is bad to begin with, so we don't really give a lot of weight to the 10-day fit. However, at 4 and 7 days, we can't ignore the fact that we are not able to produce enough blue band flux to match the AT2017gfo spectra. So what do we try from here? Oh, sorry. So yes, just to recap, we saw this in the light curves as well. We saw this about 2 magnitude difference, and we saw in the spectra. So we've confirmed that there is indeed an issue. It wasn't just an artifact of our fit in the light curves. In both the light curves and the spectra, we see the same thing happen, which means that this is a persistent problem, and we've confirmed that there is indeed a modeling issue that we need to address. So our approach is initially to start with a toy model. And this is a toy model from the Metzger 2019 Living Review, which basically is just a black body flux calculation for a kilonova. And what it's saying, so is here in equation 1, it's effectively saying that the energetics of our third component. So we're going to be adding a third component, assuming it's a radioactive heating source like the first two. So we're not going to change anything in terms of how we approach the problem, other than we're going to include a third radioactive heating component, which we want to boost the blue flux in our spectra. And the way that the energetics of this third radioactive heating component would work are as follows. The first term on the right-hand side is just energy lost from the system due to the expansion of the ejecta, so work done by expansion. We have the luminosity, which is lost via thermal cooling of the ejecta as it releases photons. And then we have an input energy from the radioactive decay of the radioactive nuclei, the unstable radioactive nuclei, which I discussed earlier in the talk. So we have 2 sources of energy loss and a heating source from the radioactivity being deposited into the ejecta. The total luminosity that's being emitted by this component, this toy model component, is simply just looking at all the different mass shells which travel at different velocities. So it's just effectively integrating over the velocities and looking at the total contribution of the component. That's equation 2. In equation 3, we can use the total luminosity in the Stefan Boltzmann law to calculate the effective temperature. And then this effective temperature using equation 4 to basically calculate in the Planck function to calculate what the black body flux is. We'll note that the effective temperature and the photospheric radius change as a function of time. The photospheric radius, of course, changes as a function of time because the ejecta is expanding, and the effective temperature changes because the system is cooling and largely losing energy. On the right-hand side, we can see the examples for the light curves for some representative bands, which are similar to what we are looking at. On the y-axis, we have AB magnitudes at 100 megaparsecs as a function of time and days. And on the top, we're looking at a lanthanide-rich, quote-unquote, red kilonova. And because this kilonova has lanthanides, it means that it was more neutron-rich, and therefore heavier elements were synthesized. And these lanthanides specifically have higher opacities, which means that there is more of the photons are absorbed from the system, are not emitted by the system. They're absorbed and reprocessed. And on the bottom, we have a lanthanide-free blue kilonova. And we can see that in general, these are actually brighter, with the exception of the K band, than the lanthanide-rich kilonova. So there are fewer lanthanides here. There's a lower overall opacity, which means that higher energy photons at lower wavelengths will escape the system. So this is what we want, right? We want something, if we look at this V band specifically, that's closest to our G and R bands. This peaks brighter and is generally brighter for the lanthanide-free version than the lanthanide-rich version. So we want something with a low opacity as our third component. So we do that. We create a black body. Sorry, before I move on, we create a black body spectrum with a low opacity. Any kind of ejecta mixing, it's just purely additive to the two component models that we had before. Of course, this is unrealistic because it neglects effects that might occur with the interactions of the ejecta, but we just want to see if it's a good step forward to use for a third radioactive heating component. In the top left, we see 1 day, the fit has not changed much, but at 4 days, this fit has improved significantly. We are now matching the observed spectrum much better. However, at 7 days, we start again to see some deviation, and of course at 10 days as well, but we don't really consider the 10-day fit as much. But we're seeing that at 7 days, we're again starting to see some deviation here, which means that our approach is not perfect. And to begin with, we were kind of unrealistic with our implementation of the toy model because we can't just simply add flux to our spectra post facto and have it be a realistic representation of the system. But what happens if we take the parameters that we used for this third component and include that third component in the radiative transfer simulation alongside the initial two components? So we basically we simulate all three components simultaneously such that we have ejecta mixing and photon reprocessing. We have all the physics self-consistently contained in the simulation. What happens then? And so just to recap, we have many different spectra in the fits here, so I'll just go through them one by one. In black, we have the observed AT2017gfo spectrum. In red, we have our initial two-component fit, which we used the same approach as with the light curves. We have our three-component fit, which is using the toy model, and that's, remember, unrealistic, because we just added it simply to the two-component spectrum. And then the most realistic case of the three-component implementation is this realistic model where we ran it alongside the initial two components in the same radiative transfer simulation and saw and got all the physics effects that would be involved with including all three components. And interestingly, what we see is that at 1 day it's not as obvious, but at 4 days it becomes obvious that our blue fit, which is the realistic implementation of the third heating component, is less bright than even our initial two-component fit. And it really starts to show at 7 days where there's a significant difference. We have effectively removed flux from the GNR bands, which is the exact opposite of what we wanted to do. So A, it's clear that this approach did not work, but B, the reason why that we think this might be happening is that the elements that we added with this third component actually increased the opacity in the GNR bands, absorbing the photons that would have been originally emitted in the two-component model, and then reprocessing them to lower energies, or as you might think, higher wavelengths, which is why we actually see this boost in the J, H, and K bands starting at 4 days, propagating in 7 days, and really showing at 10 days. So we effectively took photons from the GNR bands and moved them to the infrared bands, which we didn't want. Our two-component fits were decent. I mean, they were good. They were good enough in the infrared bands. We didn't really want to adjust that. So it's clear that for what we're trying to fix, which is this blue underluminosity, a third radioactive heating source is not the answer. So where do we go from here? What are some alternative things that we can consider? Before, I talked about YE at the start of the talk, and I've been kind of referencing it. Again, it's the neutron richness of the system, 0 meaning extremely neutron rich, and 0.5 meaning comparable amounts of protons and neutrons. And what I mentioned also is that our dynamical ejecta, so here for now I'll just focus on these red vertical lines. Our dynamical ejecta, which is the dashed line, has a YE of 0.04, and our wind ejecta has a YE of 0.27. And so they're just single fixed values. But what this plot in the background with the blue lines is showing from the Kiuchi et al. 2022 paper is that actually the neutron richness of each of these two components is more of a distribution. And it's saying that some fraction of the mass out of the total ejected mass contains quite a large range of YE values, which means that the ejecta is not homogeneous in its neutron richness. So even though we have our dynamical ejecta with a YE of 0.04, which is where their distribution peaks, there's a significant amount of the material that's actually also represented by higher YE values, meaning lower neutron richness, and that this would create more lighter elements in the dynamical ejecta. And vice versa for the wind ejecta, we're close to where their peak is for the wind ejecta, but they also show that, for example, a lot of the wind ejecta also has material at lower YEs, which means that we might expect heavier elements being synthesized in the wind ejecta. That's all to say that the nucleosynthesis yields from using a distribution of YEs to represent our components would be different, and therefore, depending on which nuclei are made, the radioactive yields then are different, and so the energetics of the system might change significantly, and therefore change how our spectra and our light curves come out from the simulation. So going forward, what we want to do is actually create compositions for our simulations which are influenced or informed by a YE distribution rather than single YE values. So to conclude, we were able to interpolate our kilonova light curves with a Gaussian process. That was our first step of making them more computationally inexpensive. We noticed that there's some blue underluminosity in the G band initially there, where even at about 3 days, we're about 2 magnitudes off, and we realized that that's a significant underluminosity. We verified that the same thing happens in spectra by creating a random forest interpolator for the spectra, and seeing that we indeed at roughly the same time see a significant underluminosity in the spectra as well. So we've confirmed that it's not just an artifact of the Gaussian process or the fit to the light curves. It is indeed prevalent in both of our approaches with light curves and spectra. We tried to remedy this by using an unrealistic toy model to create a third radioactive heating source component. It was unrealistic because we simply added it post facto to our 2-component spectra. But we started with that just to see whether it would lead us in the right direction. And it did at about 4 days, but we saw that at 7 days, it started to fall apart. So we knew that we needed to have a realistic implementation of the same approach in our radiative transfer simulations. When we did that, we actually found that we got the opposite effect of what we wanted. We were removing photons from our GNR bands and boosting infrared flux, which we did not want. But even without the boosting of the infrared flux, we went even dimmer in the GNR bands, which is not what we wanted at all. So going forward, it was clear that a third component being a radioactive heating source was not the correct modeling approach. This meant we had to consider something else, which in the short term is going to be seeing how our composition changes, how the compositions that we assume for our kilonova simulations change when we have YE representing the ejecta not be a single value as we currently do, but rather a distribution which might introduce elements which our assumptions would not have in the nucleosynthesis, and therefore see how the energetics and the observables like the light curves and the spectra change when we use the compositions derived from YE distributions. So with that, I'll finish. Thank you for your time, and I'll take any questions.
Thank you, Marco, for this very interesting lecture.